In our solar system, we have a problem, a plague on all our planets and moons.
The inner solar system's like a shooting gallery. It is a clear and present danger.
Craters, impact sites, everywhere you look.
If a big one hits, we all die.
The offenders? Asteroids, lumps of rock, metal, or both. Some older than the Sun. Many from the asteroid belt, a teeming mass of rubble lying between Mars and Jupiter, pieces of a planet that never formed. And comets, remains of the early solar system, lumps of ice and dirt from beyond the planet Neptune.
But the thing about asteroids and comets is that they're small, so they have orbits around the Sun that can change. Now, obviously no orbits are circular, they're all elliptical, but the planets and most of the asteroids and comets have orbits that are very nearly circular. But if you perturb one of those, that ellipse can become much, much more eccentric, much longer and thinner. And that can bring asteroids and comets quite close into the Sun. Now, if that happens, of course, then planets and their moons can get in the way. And that's when we get hit by stuff.
So why does the Earth appear to have no craters? Are we somehow special?
Well, the reason that there appears to be a lack of craters on the Earth is, of course, because of our atmosphere. When a small object hits the top of the atmosphere, then the air resistance slows it right down. The object will either burn up through friction or break up. Well, the atmosphere protects us only from the little ones. Of course, it has absolutely no effect whatsoever on the big ones. But even when you do blow a crater on the Earth, the wind, the rain, erosion, all those weathering processes all combine to wear it away again.
So what would happen if we were hit by a big one?
An asteroid would be hitting the Earth at somewhere between 15 and 20 kilometers per second. When a 10-kilometer sized rock hits the ground, the rock itself simply vaporizes. So what you get is a nice big explosion under the ground. That blows a crater, and if your rock was about 10 kilometers across, you'd expect a crater about 200 kilometers wide. The heat and the blast from the explosion itself is going to take out, well, certainly the area of a large country. The material blown out in that explosion is what really does the damage. You set the sky on fire, which means on the ground underneath, of course, you're under the grill. And it'll also set fire to forests and brushland globally. The smoke and the soot from those brush fires then combine with the dust that was blown out in the atmosphere to simply blanket the planet. Add all of that together and we have a really bad day.
The last time this happened, it wiped out the dinosaurs. Is there anything we can do to avoid the same fate? The first step is to scan the skies for anything that could pose a threat.
But what we're actually looking for, of course, is something that moves. Asteroids look like stars, but because they're members of the solar system, they move relative to stars. Now, what I've got here are 3 images, all of the same bit of sky, but those were taken 2 or 3 minutes apart. And if we get the computer to stitch those 3 together, align all the stars, and then play them back one after another, well, can you see the object move? If you look very closely, that fella there. Once we've found one of these things, then clearly the next thing we need to know is where it's going.
So far, we've discovered many thousands of these near-Earth objects. The majority of them should give us little to worry about, but currently there are over 200 that we have classified as potentially hazardous.
One's called 2004 MN4 Apophis, about 800 meters across, and in 2029 it's going to come exceedingly close to the Earth but not hit it. But the Earth will change its orbit, and we don't know where it's going to go after that. So there is a possibility that it could hit in 2036.
If we were to confirm one was heading our way, then is there anything we could do to stop it?
But once you know what its physical properties are, then you can develop a countermeasure. The first option is to go for the sort of Bruce Willis approach. You know, let's try and blow the thing to bits. All you've done is converted a single, predictable bullet into an unpredictable shotgun blast. The second option is much simpler and much more elegant. All you've got to do is give the thing a tiny little nudge, just enough to guarantee that it misses the Earth. Now, while this is a very rare event, it's the only natural hazard we know of that puts the future of our entire species at risk. But it's the one natural hazard that we can predict, and as we've discussed, we can make it go away.
Halley's Comet, Comet Hale-Bopp, and Comet Ison. What's the deal with all these comets, and why all the excitement? Well, for starters, comets were formed in the very early solar system, about 4.5 billion years ago. They're just like time capsules that can tell us what the solar system was like when Earth was just a baby planet. Earth, right here, orbits the sun once every year. Comets, on the other hand, come from the very farthest parts of our solar system, past the orbits of Jupiter, Saturn, Uranus, Neptune, from a place called the Kuiper Belt. Right here. Sometimes comets come from even farther out in our solar system, from a place called the Oort cloud. Our journey through the solar system takes us almost 800 million kilometers out to the Oort cloud, which on this scale takes us 2.5 kilometers down the road. Every once in a while, one of these comets goes astray and makes it into the inner solar system in a very elliptical orbit, just like this. We can create a fairly simple model of a comet using materials we find right here on Earth. Comets contain mostly ice, so I'll add some water. Minerals and dust containing some heavier metals are also found in comets, so I'll add some soil to represent those. Organic materials of carbon, hydrogen, and oxygen are going to be represented by corn syrup. This window cleaner here contains ammonia, which comets have too. And finally, the carbon dioxide here in its solid form that we call dry ice. So this is what we get, a dirty snowball. This is called the nucleus of the comet. You can see it's uneven with pockets of gas inside covered in dirt. When this comet gets close to the sun, the heat and solar winds actually start to break the comet apart. The ice sublimates into gas as it heats up, and a tail forms behind the comet, always pointing away from the sun. A second tail is also formed from the dust particles being left behind as debris along the curved orbit of the comet. If a comet can withstand the gravitational force and the solar winds trying to pull it apart as it goes around the sun, it'll often return to us to put on a show in 200 years or less. For example, the well-known Halley's Comet last visited us in 1986 and returns every 76 years. Where will you be in 2061 when it returns?
Ian Wright. Pleased to meet you.
And you.
Not the other Ian Wrights.
I'm just a mere Ian Wright.
Just a mere Ian Wright. Professor, doctor, both of those things, but Ian Wright for today. What is this?
This is a 3D shape model of something called 67P, or Churyumov-Gerasimenko. It's a comet that the Rosetta spacecraft has been tracking now for several months. Indeed, we set off 10.5 years ago to get to this comet. And we're getting closer now. We're about 30 kilometres away, and in a few weeks' time, we're going to try and land on it.
Sorry, rewind that bit. I mean, which bit? Because it looks like a kind of mushroom crossed with a nuclear explosion. It doesn't look very landable.
Yeah, it is a bit scary for landing on, and at some point we will actually, do a manoeuvre which actually drops part of the spacecraft, a little lander called Philae, off the main spacecraft and down onto the surface. And the reason is we want to know what it's made out of, or at least I do. That's my personal interest.
And you've been involved from the beginning.
Yeah, I still have the designs for my instrument. Like they're not exactly the back of a beer mat, but they're a sheet of A4 paper sketched in biro, and that has the date of 1993 on it.
You know, I've had kind of projects before where it's going to end a month later, and that seems like a long time. Waiting 10 years must be phenomenal.
It's a strange thing. I don't like to give the impression I've been sitting at my desk with my feet up, you know, drumming my fingers. We've had plenty of other things to do. Not least of all, I think perhaps people don't really understand that in actual fact, when you launch a spacecraft, there's still a lot of things to do with your actual instruments and so on that you haven't yet done. Because you know you have plenty of time to do them back on the ground, and it may be that you actually redefine the ways in which you operate the instrument, and then of course you telemeter that data up to the spacecraft and upload some new software, etc.
The parameters and all of this, and just the numbers involved, just phenomenal. There must be 1,000 things that can go wrong every day.
Yes, it is a risky venture, space exploration.
Expensive?
It's expensive, but you know, it's not that expensive when you think about the number of people it actually employs, and of course the spin-offs that come from it. I mean, that's not necessarily why we do it, but there is a payback in many different ways. I mean, certainly our instruments that we developed and the people that we trained to make those instruments are now working in all different kinds of areas, all walks of life.
What do you think it's made of?
Well, we kind of know what we think it's made out of. We know it's made out of water, ice, and the black surface is because it's covered in organic compounds. And so that, you know, what we want to know is the detail of that. And in particular, we're interested, for instance, is the water that makes the ice in any way related to the water on Earth? And we can do that with some very specialised measurements that we're going to make. And of course, if we can make that connection, then we can look at the black stuff and say, well, those are the kind of organic materials that came down to the surface of the primitive Earth from which life ultimately developed. So it's like we're kind of looking back in time to a point before life existed, at the very ingredients from which life evolved. And that's quite a fascinating thing.
Huge. I mean, good luck seems too small a thing to say. But good luck.
Okay.
The Deep Space Network, landing probes on objects moving 15 kilometers a second. This is science. Fact, you're talking. Mm-hmm. Sounds like science fiction.
Yeah. No,
this is your job.
It's the day job, yeah.
Hi, my name is Koen Geurts. I'm the Rosetta Länder Philae Technical Project Manager and I'm working at the German Aerospace Center DLR in Cologne. Today I will be explaining a little bit about Rosetta Länder Philae by using this 1:2 scale model here. What you're currently seeing is Philae in the on-comet configuration, but at the moment Philae is still attached to Rosetta in its cruise configuration. This means that the 3 landing gear legs that you're seeing are retracted and folded towards the main body. At the moment of landing, what will happen is several hours before landing, Philae will be separated from Rosetta. It means that Rosetta will push Philae off. Some point during the descent, the landing gear will be unfolded. This will allow for the legs to deploy and Philae is ready to land. What you're seeing here is one of the 3 Philae feet. Philae is supposed to touch down, of course, first with its feet. In particular, what you're seeing here is the Philae eye screw. All 3 feet have one of these eye screws that is integrated as part of the general foot, which will be penetrating the comet's surface, depending on surface hardness, of course, only driven by the impact of the touchdown. And what will happen is the eye screw will rotate and penetrate into the surface in order to fix Philae onto the surface. All 3 feet also have a scientific experiment integrated. In the soles, there are transmitters and receivers as functioning as a seismographic instrument. So the feet will be able to communicate from one to the other, transmitting sounds from one feet to the other, but also to listen to the comet and see if the comet, if there is any cracking or any other seismic activity. So as you can imagine, the comet gravitational attraction is not very high. So there's actually the risk that Philae bounces off the comet's surface in case there is a relatively hard impact. Of course, this is not something that we want, so we took some measures to avoid this. And one of them is what you see here, a harpoon. Philae actually has 2 harpoons mounted on the landing gear that will be shot into the comet upon the touchdown signal, and they will penetrate the comet, depending on its hardness, up to 2 meters. A cable is attached to the harpoon that will be rolled back and tighten the lander onto the comet's surface. In addition to the 2 harpoons, Philae has another device available to make sure that it will not bounce off the comet's surface. And this is a thruster which is mounted on top of Philae in order to thrust Philae onto the comet's surface. It will ignite at the touchdown and it will thrust for about 1 minute after touchdown. Philae cannot directly communicate with Earth, so for communication we heavily rely on the Rosetta orbiter to relay information from Philae back to Earth, but also commanding from Earth towards Philae. And for this purpose, Philae has a radio frequency transmitter and receiver mounted on the top, so that when Rosetta is passing and flying over Philae, a communication link can be established and the information can be exchanged. Relaying information from Rosetta back to Earth will take about half an hour of signal travel time, so everything which is happening on the comet will be known on Earth only about half an hour later. One of the Philae instruments is a drill, which you can see here. The drill has the capability to drill up into the comet's surface up to about 30 centimeters, and the tip of the drill has a sampling device that will be able to sample little comet parts. After sampling, the drill retracts back into the Philae main body with the sample inside, which is then deployed into small ovens which are mounted behind the drill and can then be rotated under different instruments so that the properties of the sample can be determined. So why are we taking comet surface samples? Well, simply because you want to learn and know what comets are made of. So the drill can of course take samples at different depths, but in addition, Philae has the capability to rotate its body for the full 360 degrees, which allows the drill to take samples at different locations. The instrument that you're seeing here is a comet thermometer, which at the moment is located inside the main body of Philae. At some point after landing, it will be deployed onto the comet's surface through this mechanical deployment system. What you're seeing here is the moment when it's just about to be hammered into the comet's surface. And this is done through this hammering device on the top of the thermometer. There's an electromagnetic device inside which will lift this weight up and down, and through this movement it will hammer the long thermometer, it's about 30 centimeters, completely into the comet. I'm sure that you, just like us, are very interested to see what the comet's surface actually looks like in detail. And for this reason, Philae has 7 panoramic cameras mounted around the body, which will give Philae the possibility to take a full 360-degree panorama image of the surface near to Philae, up to the horizon, perhaps even a little bit of space, and that is then used to look into detail what the comet looks like. In addition to the panoramic cameras, there's also a camera mounted on the bottom of Philae, which will take images whilst we are descending with increasing resolution while we're getting closer and closer to the comet's surface, which will give unprecedented images never seen before. Philae is also equipped with an additional set of antennas that are not used to communicate with Rosetta, but are part of an instrument which is located both on Philae but also on the Rosetta orbiter. And the two instruments, the two antennas, communicate with each other, not when Rosetta is inside, but when Rosetta is at the other side of the comet with respect to Philae, and the radio waves are traveling through the comet so that we can derive the properties of the inside of the comet. The mass of Philae is about 100 kilograms, and Philae is equipped with batteries in order to provide energy during the descent and just after landing, but in addition, solar panels are located all around the main body and on top of Philae in order to operate, hopefully for several months, on the comet's surface.
It is a mission of challenges. We've already been through several hurdles already, and to some extent we're very pleased to have come over them. So yes, I mean, there's the wake up on the 20th, then we have to ultimately start switching our own instruments on, see if they still work. We then have to look at the comet, see if it's possible even to land at all. Then we've got to get down on the ground. Then we've got to find out if our instruments have survived it to the ground, and then we've got to start acquiring the data. So there's lots of times when one's heart could be beating quite quickly, I think. I mean, what we're particularly interested in is questions such as, what are the relationships between the materials that comets are made of with equivalent materials that we find on Earth or in other parts of the solar system? And water is a good example there. We know that comets are made of water ice. But what we're interested in, is there a relationship between the water in comets and the water that we find on Earth? In other words, did comets actually bring that water to the surface of the primitive Earth? And if we can assess whether that's true or not, we can then start looking at the other components that are in the comets, the organic compounds and whatever else, and begin to sort of get a picture of what primitive organic compounds were brought to the surface of the early Earth as well. And clearly at that point we're looking back in time at a period before life had got started on the Earth, but we're beginning to look at the actual building blocks of biology on Earth. What this instrument does is it will be involved with a campaign where solid samples are drilled out of the surface of the comet, delivered into the spacecraft, and then they'll be put into an oven connected to this instrument. The oven will heat the sample up, and all the materials that are in there will then ultimately go into this instrument, and this will tell us what the comet is made out of. This is a scale model of the lander. The lander's called Philae. Normally it is completely covered in solar panels. They are taken off so that we can see the insides here. And as I say, this is a scale model. The real thing I always say is about the size of a washing machine, so that gives you some idea about how big the whole lander is. And our instrument that we saw in the laboratory is actually buried deep inside here. The way it gets samples is through this device here, which is a drill, which goes down into the surface of the comet, brings the materials up. They then get put into an oven round the back here, and that gets rotated into mating with our instrument. Once you've developed sophisticated instrumentation that is literally the size of a shoebox, you then have potential applications that you would never have had previously with laboratory-sized instruments, either because they're too big, they're too heavy, you can't wheel them around. And so the applications are in any number of areas. They could be in pollution, in global climate change issues, or in healthcare, which is something that we've been exploring. So we've been involved with a number of studies involved with applications in TB detection, cancer detection, and so on. In some ways, some of the applications are way more surprising to us than we'd imagined at the start. I think all of us who've been involved with it over these years are quite grateful that we've got to, that we are getting to this point, the point where we're actually going to do the things that we set out to do. It is nerve-wracking, of course, because there are plenty of things that could go wrong, but it's what space exploration is all about.
We want to reach our target. Our target is a comet. The team has expectation from you every day, and you always have to think ahead. You cannot come in the morning and say, what do we have to do today? You always have to think well ahead.
If Rosetta doesn't wake up, our mission will already be over. Our fingers are crossed for the first signal to make it to Earth.
On the day of hibernation exit, there was high expectation that we'd successfully come out of hibernation. When that time in the morning occurred, you think, well, okay, that's it now we just wait. So you wait for the spacecraft to stop spinning, to warm itself up, and to get ready to send this signal.
Hello everybody and welcome inside the main control room, which is quite exciting. We also get a good view of the countdown clock here before Rosetta will wake up.
It requires 45 minutes for the signal to travel at the speed of light to come from the spacecraft to us.
That's a big success for everybody. Now we got it back. Now it's up to us to drive it to the comet.
You want to see this clean peak, and that's what we got. You wait a few more seconds and you see this clean carrier signal, and that's all you need to know.
We have no idea what is waiting for us out there. Rosetta will use its navigation camera as it gradually closes in on its target, Comet Churyumov-Gerasimenko, before shifting to the trajectory that will finally bring it to its destination. Then it will start to orbit the comet, map it and characterize it. This will enable us to search for a landing site and land the Philae lander in November 2014. Philae is the part of the Rosetta mission that will land on the comet. So we will really have the opportunity to investigate the primordial dust and ice material on site.
You've got to watch yourself here. This is what we're looking at. 50% of the comet's going to be made of material like this. We can look at the water on the ocean of the Earth and compare that ratio to what we find on comets. Whether it's like sheet ice or it's more dusty ice, possibly this water could have been delivered to the Earth by the comets. This is why we're going to this comet, to see where that water comes from, to see is it connected to Earth at all? And that's then connecting to whether we ourselves are connected to comets maybe, who knows?
With this mission, we're entering new territory. In Berlin, we have built 3 instruments for this lander. The Rollis camera on the bottom of the lander will acquire 6 or 7 images that will reach Earth hours later. The MUPUS device will be hammered into the surface to measure the thermal properties. These will then be refined using the other instruments to understand what kind of environment we've landed on.
The spacecraft is now on a trajectory to the comet, but it doesn't have yet the right velocity to actually arrive at the comet and stay there. We activate our thrusters, the small rockets we have on board, and we accelerate the spacecraft to reach the exact velocity of the comet. And we do an acceleration of about 800 meters per second. It's a lot of acceleration.
We start to see this pinprick in the distance, and then you realize this is reality. It's not a theoretical concept anymore, it's a real comet. We're seeing this pinpoint of light getting closer and closer. It wasn't like this grey potato that we first imagined, that it was actually much more interesting.
It consists of 2 parts. This double structure was not expected, and we all had the same initial thought. How will we land on this? It hasn't made things any easier. We don't want Philae to end up on its back like a beetle or to crash. All these things are much easier to solve on a spherical target than on a very rugged surface with valleys, even canyons, cliffs and crevices. These are difficult conditions.
Therefore, we have a ground reference model here at the Lander Control Center to test all the sequences over and over again. It takes some time, but we have to make sure that it works. The landing sequence will be started at a specific moment. At the same time, the orbiter must adopt a specific orientation, as the lander will be pushed away from the orbiter. As soon as the lander's feet touch the surface, 2 harpoons will be fired to anchor it. To further secure the lander, ice screws on the feet will then draw it towards the surface. One must prepare as best one can.
We will spend the time in characterizing the comet.
We have the faintest idea of the gravity potential of the comet, of the gravitational forces. So we have to measure them, and then we can orbit the comet.
And there we will start mapping. We need to do a very good map to decide where to land.
All these, we have to do it before, otherwise we are not even able to discuss about lander delivery.
So it's a massive challenge technologically, but at the same time, the reason we're at this comet is for science. No other reason. We're doing this to get the best science, to characterize this comet as has never been done before.
What will be interesting for the scientists will be to observe the changes, what the comet does as it approaches the sun, becomes increasingly active, and starts to outgas and form jets.
Parts of the comet's surface are dead and inactive. Nothing is happening. And there are some places where plenty is going on now. At the moment, some 500 grams of water per second are outgassing from the comet. Closer to the sun, this will rise to 300 kilograms. What would happen if the lander were to touch down in one of these places? It would probably not guarantee a long operating life.
If we target an active area, an area where there's lots of outgassing, sublimation, so lots of material coming off of the surface, it's going to be difficult to get the lander down there.
After considering all the different aspects of the possible landing sites, we have decided on landing site J. We've also selected an alternative landing site C on the body.
This undertaking is so complex that a single person would be overwhelmed by it. It simply isn't manageable. It's only possible in large teams. You have to get together and discuss. And the good thing is that they're all great people, people with their feet on the ground who you can really talk to.
It presents particular challenges, but ultimately Rosetta shows you what you can do by collaborating internationally. It's just great to be here. It's great to be involved in this and be involved with the scientists, the guys that are doing this. To be able to interact with people like that that's it.
You can imagine how privileged we feel to be the ones to have to land this object on the comet. But at the same time, you can understand the level of responsibility that sits on our lands and to our shoulders. We've spent years with the colleagues of the lander team, mainly the colleagues from CNES and DLR, to work out strategies, to redefine them, to trade them off, to negotiate them, to fit all the constraints and the objectives we have for this operation phase. And now we have to implement it for real. Time has come to make it happen.
Activation on ready. Characterize the power. Very cool. Very, very slowly.
On November 12th, this animation should become reality. The Rosetta mission will achieve a first when the Philae lander touches down on Comet 67P Churyov-Gerasimenko. As a space scientist working with those who have instruments on board this lander, I'm going to take you through 5 of the questions I'm always being asked about the Rosetta mission. And I'll be meeting the OU experts who have all the answers. I guess it's just the irresistible curiosity of humans. We simply just have to know what's out there. But actually, there are some fundamental scientific reasons to visit a comet too. So why do we bother going to a comet?
Well, we want to go to a comet because it's there. It's an object in our astronomical backyard, and we want to know what it looks like and what it's made out of.
And from my own research, I know that comets contain organic material and water. What are we going to learn from Rosetta about this?
We want to know whether the water in a comet has a relationship with water on Earth. And if it does, we then want to study the organics in the comet to know something about the organics that were brought to the surface of the early Earth.
Harpoons in space, who would have thought? One of the things about this landing is that it's nothing like any other landing to date, on a planet or a moon. So Andy, why do we need harpoons on the Philae lander?
There are 2 harpoons on board, and it's the first time it's been used in space because the gravity of the comet is so low, so it's used to attach the lander to the surface.
So are the harpoons just required for the landing sequence?
Not just the landing sequence, but throughout the mission, the comet's going to become more active, gas is going to come off, try and push the lander away from the comet, so it's to keep it firmly attached throughout the whole of the mission.
Well, actually, it's not an oven big enough to cook your pizza, but instead a version of a lab instrument that's to heat up samples for analysis. So Simon, where are the ovens on board the lander?
Yeah, there's a number of ovens on the instrument. They're located behind this drill on a circular carousel, and the ovens themselves are these little devices.
Why do we need ovens?
Well, the OU's instrument is a mass spectrometer, and we need to analyse gases. So we take the solid cometary material, pop it into the oven and heat it up, and we get the gases off that we can analyse. The Open University's instrument, Ptolemy, is located inside the lander, and it's actually located in this compartment here. So this is Ptolemy, and the gas from the oven is led via pipe into here for analysis.
I'm always being asked this question because it's possible that Philae will not land successfully and that the instruments may be unable to work. But what would happen to the mission then?
The instruments, including Ptolemy, and this is a life-size version of Ptolemy,
are already pre-programmed, and so we will sniff the comet whatever happens, whichever way we land.
Oh, that's brilliant. So how does this Ptolemy model you're holding relate to the lab one we're standing next to?
Well, as you can see, it's a miniaturization of this whole system and has very similar functionality. And we've been applying the know-how that we developed in producing Ptolemy to several challenges back here on Earth. That's included healthcare, safety equipment, and also even measuring the quality of our drinking water.
This could seem like a bit of an overclaim, but is it? We only have to think back to the demise of the dinosaurs, who were likely killed off by a comet colliding with the Earth.
Could this mission save the world? Well, not directly, no, but it could indirectly. Comets travel through the solar system all the time. Some of them come very near the Earth, some might even have hit the Earth in the past. Now, the more we know about comets, their composition, how tough they are, how easily they break up, the better it is, so that we can understand more about deflecting them away from the Earth. It might sound like science fiction, the idea of deflecting a comet, but if the choice is between science fiction and global devastation because a comet hits, what choice do you have?
Blown out in that explosion is what really does the damage. You set the sky on fire, which means on the ground underneath, of course, you're under the grill. And it'll also set fire to forests and brushland globally. The smoke and the soot from those brush fires then combine with the dust that was blown out in the atmosphere to simply blanket the planet. Add all of that together and we have a really bad day.
The last time this happened, it wiped out the dinosaurs. Is there anything we can do to avoid the same fate? The first step is to scan the skies for anything that could pose a threat.
But what we're actually looking for, of course, is something that moves. Asteroids look like stars, but because they're members of the solar system, they move relative to stars. Now, what I've got here, the thing about asteroids and comets is that they're small. So they have orbits around the sun that can change. Now, obviously, no orbits are circular, they're all elliptical, but the planets and most of the asteroids and comets have orbits that are very nearly circular. But if you perturb one of those, that ellipse can become much, much more eccentric, much longer and thinner, and that can bring asteroids and comets quite close into the sun. Now, if that happens, of course, then planets and their moons can get in the way. And that's when we get hit by stuff.
So why does the Earth appear to have no craters? Are we somehow special?
Well, the reason that there appears to be a lack of craters on the Earth is, of course, because of our atmosphere. When a small object hits the top of the atmosphere, then the air resistance slows it right down. The object will either burn up through friction or break up. Well, the atmosphere protects us only from the little ones. Of course, it has absolutely no effect whatsoever on the big ones. But even when you do blow a crater on the Earth, the wind, the rain, erosion, all those weathering processes all combine to wear it away again.
So what would happen if we were hit by a big one?
An asteroid would be hitting the Earth at somewhere between 15 and 20 kilometers per second. When a 10-kilometer sized rock hits the ground, the rock itself simply vaporizes. So what you get is a nice big explosion under the ground. That blows a crater, and if your rock was about 10 kilometers across, you'd expect a crater about 200 kilometers wide. The heat and the blast from the explosion itself is going to take out, well, certainly the area of a large country. The material are 3 images, all of the same bit of sky, but those were taken 2 or 3 minutes apart. And if we get the computer to stitch those 3 together, align all the stars, and then play them back one after another, well, can you see the object move? If you look very closely, that fella there. Once we found one of these things, then clearly the next thing we need to know is where it's going.
So far, we've discovered many thousands of these near-Earth objects. The majority of them should give us little to worry about, But currently, there are over 200 that we have classified as potentially hazardous.
One's called 2004 MN4 Apophis, about 800 metres across, and in 2029 it's going to come exceedingly close to the Earth but not hit it, but the Earth will change its orbit, and we don't know where it's going to go.
In our solar system, we have a problem, a plague on all our planets and moons.
The inner solar system's like a shooting gallery. It is a clear and present danger.
Craters, impact sites, everywhere you look.
If a big one hits, we all die.
The offenders? Asteroids, lumps of rock, metal, or both. Some older than the Sun. Many from the asteroid belt, a teeming mass of rubble lying between Mars and Jupiter, pieces of a planet that never formed. And comets, remains of the early solar system, lumps of ice and dirt from beyond the planet Neptune.